2 degrees or 4 moon widths away from the ringed planet. For Northern Hemisphere observers, Jupiter is visible at sunset for the first week of November, but then it becomes lost to view on November 26th as it reaches solar conjunction. Solar conjunction is when the Sun is directly in between Earth and another planet. Next month, Jupiter will reappear as a morning planet. Mars has its own meetup with the Moon. It continues to be brightly visible in the evening sky. As it moves farther from Earth in its orbit, it will fade in magnitude and shrink in apparent size. Mars will be easy to see on November 26th when NASA's InSight mission lander touches down on the red planet. Asteroid 3 Juno, the third asteroid ever discovered, but only the 11th brightest, is visible in telescopes this month, shining at magnitude 7.5. Comet 46P, also at magnitude 7.5, may brighten to naked eye visibility. Observers in both the northern and southern hemispheres should be able to see it. Finally, the Leonid meteor shower peaks November 17th as dust from Comet 55P Tempel-Tuttle passes close to Earth. The Leonids are best seen after midnight your local time, once the moon has set. You should also be able to see some Leonids on the 18th, 19th, and 20th. The maximum for any of these nights is only 10 Leonids per hour. Next month we'll wrap up the year, and I'll wrap up 12 years writing and presenting What's Up. A new presenter will resume the series in January. You can catch up on all of NASA's current and future missions at www.nasa.gov.
The night sky is never truly dark. If you removed light pollution, the moon, stars, and galaxies, there would still be a very faint, colourful glow. That's air glow. With cameras, you can photograph it only on the darkest of nights. It's about 1/10 as bright as the combined light of all the stars. From above, it forms a luminous bubble encapsulating Earth. Appearing right at the interface to space, airglow holds clues to how our atmosphere affects weather in space, and how space weather affects humans on Earth. The bands of light span from 50 to 400 miles above Earth's surface. In the uppermost boundary of the atmosphere is the ionosphere. This is where our GPS signals and astronauts travel. What makes this region complicated is that it's constantly changing. It reacts to both energy emanating from the sun and weather near Earth's surface. And as the ionosphere fluctuates, so can conditions in near-Earth space where the space station lies. But spotting changes in the ionosphere is a lot like trying to watch the wind. You need a marker of some kind to see the invisible particles move past. And for that, we have airglow. These colourful lights reflect changes in the ionosphere, and this is due to the way it's formed. Our atmosphere consists mainly of nitrogen and oxygen, and small traces of other molecules. When these molecules reach the upper atmosphere, they're at the mercy of the sun. Ultraviolet radiation from sunlight excites them. They become energized and need to release that extra energy in some way. Atoms that remain energized long enough can emit that extra energy through light. In the lower atmosphere, we don't see as much light. The atmosphere there is dense. So when an atom becomes energized, there's a high chance it will bump into another atom and lose energy in that collision instead of emitting light. But as you travel further up, the atmosphere thins out. And like a game of dodgeball, the longer atoms stay untouched, the more time they have to emit a bright, colourful photon for us to see. That's why airglow is only seen in the upper atmosphere. But it can get even more complicated. Some collisions can produce light too. On the night side of Earth, green light is the brightest and occurs when oxygen atoms become excited through collisions with oxygen molecules. A variety of other complex reactions create red and blue light, as well as UV and infrared light that are invisible to the human eye. Each type of airglow contains information about the composition, temperature, and density of the upper atmosphere, all of which are key factors that can change dramatically and rapidly. So airglow turns out to be a fantastic proxy, illustrating not only how particles move through the ionosphere, but what kinds of particles even exist there, which is key information for helping us tease out how space and Earth's weather interconnect. And that's a great reason for NASA to study this beautiful phenomenon.
Although we've done it before, landing on Mars is hard, and this mission is no different. The process to get from the top of the atmosphere of Mars to the surface we call entry, descent, and landing, or EDL. It takes thousands of steps to go from the top of the atmosphere to the surface, and each one of them has to work perfectly to be a successful mission. The process starts well above the top of the atmosphere of Mars. The cruise stage faces the sun. It also has its radio antenna, which faces Earth. But now we don't need the cruise stage. Its job is done. The next step, just 7 minutes before arriving to the top of the Mars atmosphere, is to separate the cruise stage. Before you hit the top of the atmosphere, though, the space capsule has to orient itself so that the heat shield is precisely facing the atmosphere. Now the fun begins. The vehicle is moving at nearly 13,000 miles an hour, but it's hitting the top of the atmosphere at a very shallow angle, 12 degrees. Any steeper, the vehicle will hit the thicker part of the atmosphere and will melt and burn up. Any shallower, the vehicle will bounce off the atmosphere of Mars. At the very top of the atmosphere, it's about 70 miles above the surface of Mars, and the air is starting to get thicker and thicker and thicker. As it does that, the temperature of that heat shield gets well over 1,000 degrees centigrade, enough to melt steel. Over the next 2 minutes, the vehicle decelerates at a backbreaking 12 Earth Gs, from 13,000 miles an hour to about 1,000 miles an hour. At about 10 miles above the surface of Mars, a supersonic parachute is launched out of the back of the vehicle. 15 seconds after the parachute inflates, it's time to get rid of the heat shield. 6 pyrotechnic devices fire simultaneously, allowing the heat shield to fall and tumble away from the vehicle, exposing the land.